using Python for structured prediction. Thank you.
Hi, everyone. All right. So just as a quick question, just so I can kind of get a feel for the room, how many people here actually routinely use scikit-learn for tasks? And how many people have kind of heard of scikit-learn? OK, awesome. So it's like half use, all know. Awesome. So OK, so this is a talk about something that you actually really can't use scikit-learn for, but it's very much the kind of machine learning problems that I think a lot of people actually really care about, which are these structure prediction problems. And what I mean by structure prediction is I mean problems where what you're trying to predict in one piece of data is going to depend on features in nearby piece of data. And those will become more clear as I kind of go forward. Again, there's certain caveats with doing this and doing structure prediction in models. Namely, anytime you have to start analyzing interactions between your data points, you're going to have longer training times, which sucks because these are usually gigantic data sets. These are text corpuses. These are image corpora. As another kind of caveat, I'm not going to talk about the learning methods themselves. That's like an hour talk onto itself. This is just about using the libraries for doing structure prediction, not necessarily what is structure prediction and how do you do that kind of optimization. Also, this talk probably won't change your life. All right, so where do you typically see structure prediction? So it comes in places where all the data points are related. So it comes up in things like time series, where you're trying to predict something over time. It's not just about just taking all your features. Your prediction from one point to another is very much dependent on what prediction you had before. The simplest models, whether it be ARMA or RIMA or GARCH, all have this assumption of using features from your previous predictions. If you're doing web classification, you could treat it as just a binary or multi-class problem, but you can also handle the kind of interdependencies that occur between web pages, because web pages link to other web pages. So it's not just about the features in the web page that matter, it's the features in the web pages it links to, which give you this kind of superior results. It comes up in named entity recognition, when you're trying to refer whether British Midland is an organization, a location, a person, or a currency. It's not just about the word itself or features on the word. You really care about the local context. And in fact, as a regular supervised learning problem, this is a no-go. This just won't work. Now it's just to belabor the point again, just in case you thought you can kind of kludge your problem into a classic machine learning problem. Because people try. I mean, they do tricks to do this. You know, you can include features from your JSON words in the but it still fails in many particular cases. It'll fail, and it'll even fail problems that look like a supervised learning problem at first brush. So for anyone who doesn't know, I'm going to make things really sad for you. Classic machine learning breaks on when you have large numbers of classes. Just the boundaries get too sharp, and it just breaks hard. So even if you have something that at first brush looks like a classic classification problem, you probably also actually just have a structured learning problem that you didn't even realize. And you're going to have to treat as such to get any modicum of reasonable accuracy. So it comes up in this images when you're trying to classify scenes and which pixel this image comes across. Basically, the idea with this task is, given an image, say what parts are sky, say what parts are buildings, say what parts are plants, and things like that. If you just look at the pixels, you do awful at this task. You need the local context of how you're labeling the pixels around it. And really just say, really just a belabor point, this is essential to get any performance at all. Okay, so now that we know we need to do this, what should we use? I'm going to suggest as a first brush, you check out two libraries, pyCRFsuite and Piestruct. So what is pyCRFsuite? pyCRFsuite is a Python wraparound CRFsuite written by Jake. I don't think Jake's here right now. I think he went to the other talk, but you can ask him more about it. CRFsuite itself is a linear chain CRF library written by Ogazaki. Reason it's worth mentioning is that it's a very simple case. It's only for linear chains. It's only for things that occur in a sequence. So things like text and time series. It doesn't work so much on images. But because of this restriction, it is very fast, which is the reason you should care about it. Piestruct is a little more general. This one's written by another scikit-learn contributor, Andreas Müller. Piestruct wraps up has to be close to half a dozen to a dozen different solvers for solving the general structural learning problem, including libdi, 83, cvexop, qpo, et cetera, et cetera. I'm missing many things. So this is Joris, the author of libda, and this is Andre Martins, the author of 83, Eating a Potato. So now, I kind of lied. I didn't say I'm talking about it. Just to kind of give a context of what I mean by CRF, because I kind of just used it without explanation. What I mean by CRF is essentially a model where you explicitly have feature functions that connect between the labels and the observed input. This is in particular a linear chain model. That's all I mean really by CRF. It's just a model for connecting just interconnecting the different labels. Now, all these libraries are still somewhat alpha, so it's kind of a little pain to get them installed. Luckily, pyCRFsuite is fairly straightforward. All you have to do is install CRFsuite from source, and then install pyCRFsuite. I think you have to make one small patch to pyCRFsuite to make it install, which I've almost finished writing a pull request for, but that should work momentarily. For Piestruct, you got a little more work ahead of you. Piestruct has quite a few dependencies. There's no really good way I know of to easily pull them all in. You just kind of have to go through this step until Andreas adds some kind of make dependency thing. Anyway, having had them installed, for CRFsuite, let's tackle how you might do named entity recognition. So how would this task typically go? First, you should grab a data set. I realized I lost mine, so I grabbed the Hungarian one instead. The data set mostly looks the same. It's just that it's leaving off the part of speech tags. So I had to do some hacky stuff, which I put online, to go put on the part of speech tags onto it. So you'll have that available to use. So once we have that done now we have to write our features. But here's the interesting thing. In structured prediction problems, you don't have features on your terms. You have features on your terms and their local neighborhood. So what you actually will define is you'll have a feature. So the way these templates work in CRFsuite is you have a feature for the word to before this one, an indicator function for the previous word, an indicator function for the combination of a pair of words, meaning if the last two words were is this feature goes off. And then you have similar ones for part of speech. So this one's basically the local neighborhood of your part of speech going backward, part of speech going forward. But this is a very interesting thing that you can now do. You can now have arbitrary features across your local neighborhoods of words, and now you can actually start including that context to do that joint learning. In the CRFsuite library, there's a more involved part for named entity recognition that's more fancy than this. And what you can see is you can use arbitrary Python code to do this. Just whatever feature you want that's an interaction across the sequence is available to you. So we do that. So basically that was just the chunking file from CRFsuite. So I passed our data set through it to create the CRF data set. It's largely unreadable, so I haven't put it at output here. At this point, we do very scientific test train split. And then we run it. And basically, it's very straightforward. You basically just initialize the data set and add this file in, and then it runs. And basically, it gives you some informative metrics, basically just saying how loss is doing, things like that. And eventually, it finishes. And then to test it, you basically just load the model, take the model you've initialized, label your test set over it, and then just label it down. And basically, what you'll get out are these outputs. I don't think this is the cleanest thing, but I think that's going to get fixed. We're basically just going to go over each word and say what the classification was. So 0 means this is not an entity of any kind. And this org means this word was an organization. As you can see, it actually does reasonably well. I couldn't quite get interpretable numbers to put here, but I assure you this does better than the naive thing of just unary potential terms. So for PyStruct, you get a little more bespoke experience. So for the PyStruct example, I'm going to be using Andreas's toy cross example, where basically we have these crosses that we then add noise to, that we're trying to predict what the true value is. So we generate 50 of these crosses, and then we fit our model. So unlike in pyCRFsuite, in Piestruct, there are methods to auto-generate the features. So in particular, what gridCRF does is it creates features for the local neighborhood. So basically says, given this pixel, also include a feature for the pixel above it, the pixel to the left, the pixel to the right, the pixel below. And interactions as well, just pairs of a feature for me and the pixel above me are the same color, me and the pixel to the left of me are the same color, etc. So that's just automated. So all that other kind of hacky stuff is automated here. And then it gets past the learning algorithm. In this case, Piestruct supports multiple. The one that seems to work the best is the one// structured SVM. There are multiple ones, but basically what you do is you pass your model, you pass some arguments to make sure the LP solver underneath doesn't break on you, and then you let it run. This is a little slower than CRFsuite. Then once that's done, you can check how well you did. And at least for this toy problem, it did very well for the value of the toy problems have. Now, just to get a feel of what exactly it did, the idea was that's the actual thing of the ground truth was that what we actually had. Then we basically put some noise on it, and our prediction, of course, completely recovered the ground truth. Again, somewhat trivial, but at least the tests work for any of these things. But again, these are structured problems. And as we've already established, image segmentation is really hard without doing this kind of structure thing. Anyway, you can find more resources there. Structured prediction is totally doable in Python. Right now, as soon as this talk ends, there's still some legwork to make things a little nicer in both libraries, which I'm sure Jake and Andreas would love contributors. And this is where the cool stuff is going to be happening. So, questions? I'll put them up online in half an hour or so. Oh, sorry. The question was, where are my slides? And I said I'll upload them to my GitHub account in like half an hour or so. Have you played around with SVM Struct? The question was, have I played around with SVM Struct? Yes, I have. It's kind of I felt it's kind of hackish. It has the same kind of. It's hard to really kind of get it to work. What I kind of really liked with Piestruct was that Andreas kind of mucked with it until he managed to make it work consistently on a bunch of problem spaces. So I very much appreciate for that. I mean, in a certain sense, a lot of what these libraries are doing is kind of taking the next step. in a certain way that like scikit-learn took the next step of going, oh, well, we had SVM trainers before, but now we have these nice libraries for really encapsulating that pattern. This is part of that same process. Yes, we've had nice trainers before, but now we can start pushing more of that into Python and more into the language and pushing our feature extraction and our model building closer together into the same place. Any more questions?
I have a question. Do you use those tools on specific applications yourself? And can you share?
The question was, do I use these tools on specific applications? Yes, I do. I actually use pyCRFsuite for doing structure sentiment analysis. Basically, it's just this hands-free method so you don't have to do hackish things with nots, ands, and buts and other things. But that's part of just kind of ongoing research, and I'll be happy to share that very soon.
What's the field? I didn't get that.
Sentiment analysis. The question was what the field I'm referring to is in sentiment analysis. Oh, so I should be clear. You can engineer your own features. The point is, since you have these you can define your local neighborhoods as not just being adjacent pixels, but it might just be something like much more in the flavor of a Gaussian process, where you're saying kind of at this pixel and kind of in some kind of diffuse neighborhood around it, I'm going to gather these statistics. The question was about doing structured learning for geospatial. And of course, yes, it's just the feature functions changed a little bit.